Hi everyone, in this video I want to bring you a recent preprint from the Apple Machine Learning Research website, which I found very interesting, to be honest. It is the parallel track transformers, enabling fast GPU inference with reduced synchronization. So it is mentioning the fact that yes, large language models today are popular and they rely on the transformer architecture, and when you have thousands of users you need to serve them. The problem is when in serving, typically for a particular layer you split the computation across multiple GPUs, and then after each GPU performs an operation, there needs to be a synchronization, essentially combining the results involving multiple GPUs, and typically this is to reduce the issue of latency and throughput problems. The problem is that GPU synchronization introduces bottlenecks and it can degrade stability. So in here they mentioned that they have a new architecture to solve this problem. I found it very interesting. They experimented with TensorRT-LLM, which is from NVIDIA, and vLLM, which is actually a PyTorch project. So here, for example, they mentioned that they achieve up to 15 to 30% reduction in time to first token and 2 to 12% reduced time per output token, which I think is very incredible. And times 1.90 increased throughput in both settings. So let's see how it works. So in here they are mentioning, transformer-based large language models have made rapid and significant progress in recent years. Very popular, right? Everyone knows that. The problem is efficiently serving those models at really large scale is a problem, and some attempt to resolve this problem using pipeline parallelism or data parallelism. In this case, for example, splitting multiple data points across multiple GPUs, or tensor/model parallelism. Sorry, by the way, if I'm pronouncing the word parallelism, I found it a little bit hard to pronounce. Anyway, this tensor parallelism is actually the most popular, I think, which I just mentioned in the abstract. So you split a particular layer's computations. It could be attention layer across multiple GPUs. Each GPU performs the operation, tiny operation, and then synchronize the results, right? So a layer could also be a feed forward. The problem is it can introduce significant latency and it can hinder scalability. So in here is just more information about related works. Let's see how they are attempting to solve. So they introduced parallel track transformer. So instead of having a giant transformer, what they propose is, why not have smaller transformers with less dimensional layers, which they call tracks, and then perform this synchronization less often instead of after every layer. So here they mention periodic synchronization is performed between tracks, between smaller transformers, full transformers with less dimensional layers between tracks to preserve model quality. So they do this periodic synchronization to preserve the model quality while avoiding the frequent synchronization that I just mentioned. So this is the system. Instead of this giant transformer, we have smaller transformers. A track block is essentially a part of the smaller transformer. So this is the block. So you get input goes into multiple blocks, right? And a block can have multiple layers, and then perform synchronization, then continue to further layers of each block till the output. So the experiment result demonstrate that the PG transformer can significantly reduce synchronization overhead while achieving model quality compared to that of the standard transformer. This is the background, which is actually very important. Essentially here mentioning transformer-based large language models. They are very popular, achieving remarkable results, but you need to typically, when serving them, use multiple GPUs. That make using single device can be very slow. So in tensor parallelism, which I mentioned earlier, that splitting a layer across multiple GPUs, since each layer can have attention and feed forward, for each layer then there is 2 points of synchronizations, and when a transformer has L layers, there's 2 times L synchronization points. So which I'm going to show you later on, from 2L they want to essentially make it L divided by D, where D is like a track block, and a track block is like D consecutive layers inside a particular track. We are going to see that. So here they just mentioned that instead of having one giant transformer, the PT transformer divides the entire model into several smaller transformers referred to as tracks, which I just mentioned. Okay, so on page 3 here, so given a total of L transformer layers and a track block of D of depth of D, This particular approach reduces number of synchronizations from 2L to L divided by D. So I already explained how we got this 2L, and how about L divided by D. So let me step back. As I've mentioned, D is the number of consecutive layers executed independently before synchronization. For example, when D is 4, the model synchronizes once every 4 layers. Although each layer still contains attention and feed-forward operations, the PT transformers do not synchronize after each of them. Instead, they perform all computations locally for D layers and then perform a single synchronization step. So since the total number of layers is L, this results in L divided by D. L divided by D synchronization points. Okay, I hope that is clear. Let's look at and they also mentioned that because each individual transformer in PT operates at a reduced dimensionality, the volume of data exchange during synchronization is also smaller compared to dense models. And they call this track parallelism. Okay, so let's look at the pseudocode quickly. We have an input. So for each layer L, from 1 to L, which the bigger L is like the total number of layers, you run the L transformer layer for each track in parallel. And then you set this D, let's say D is 4. After 4 layers, you perform a form of synchronization. And then after that, you broadcast the results back to all the tracks and then continue the process. So here they are just comparing similar architectures or similar systems with this PT transformer that you can also read. Let's look at the experiments, which I think is very interesting. They measure latency and throughput. So the experimental with model of 6 billion, 13 billion, and 30 billion parameters. And the experimental with a model that has 8 tracks. Essentially 8 smaller transformers. So for example, they compared the results later on with like normal transformer architecture that use data parallelism. So for example, a model of 6 billion parameters with this number of layers can have 32 attention heads. So in here, instead of having 32 attention heads, you split those heads across the tracks. So each track is going to have 4 attention heads, and typically we can have 8 kV heads. So instead, each track has 1 kV head. So similarly for 13 billion, 30 billion parameter model. Let's look at the results. Remarkable. So we experimented with D of 2, 4, and 8. So they mentioned that they achieve competitive performance compared to standard dense models. So for example, when D is 8, which is an extreme case, that reduces synchronization by 93.75%, 16 times in reduction. Okay, so they have multiple benchmarks. This is the standard model. This is different settings of D. So I just want to focus on an extreme case, which is very interesting. On this particular benchmark, ARC, which is a reasoning benchmark, the extreme case actually achieved the best results. And on this CQ and Winograd, I'm not sure if I'm pronouncing it right, Winograd, the extreme case actually achieved the best result. And this human eval, which is I think is a coding related benchmark, the extreme case D of 8 achieved the best result. So D of 8 means we are actually synchronizing significantly less often. Okay, so this is for the 16 billion parameter model. This is for the 13 billion. Okay, so we are on page 5. This is for 30 billion that you can check. Let's look at the serving. They experimented with 13 billion parameter model on 8 H100 GPUs with different settings of D. They experimented with TensorRT-LLM and vLLM. So both this TensorRT-LLM is NVIDIA's optimized GPU inference engine for large language models, while the vLLM is actually a PyTorch project. Is an open source system designed for fast and scalable LLM serving. So they mentioned that this PT achieved 15 to 30% reduction in time to first token, and also 2 to 12% reduction in time per output token, which is remarkable. So I want to skip the TensorRT and go to vLLM. Still for the vLLM, the same GPU setting. So they mention improving TTFT, which is the time to first token, and also time per output token. So looking at the vLLM throughput output tokens per second, the higher the better for 30 billion parameter model. When we look at the, for example, different input lengths, different output lengths, again, I am looking at the overall. There are cases where this PT architecture achieved the best result, even at an extreme case of D of 8. And when we look at time to first token, which is when the lower the better, the extreme case when D is 8 actually achieve the best result in all of the cases. But here it's like a maximum batch size of 1. Alright, so they concluded, which is important, that we further extend this design by incorporating mixture of experts to replace the dense MLP layers, yielding the PT-MOE architecture, which is one of the major advancements highlighted in the Apple Foundation Models 2025 report for private cloud compute. Remarkable. This is page 7, the remaining and references. Alright, thank you for watching. I urge you to read the paper online. Bye bye.